400 years of systematic hunting for the hat-making industry push these aquatic rodents to the absolute brink of total extinction. Why can these small ecosystem engineers achieve what human engineering has failed to accomplish for several centuries? While artificial dams often disrupt local hydraulics, beaver activity initiates a natural sequence of reviving dead riverbeds and restoring scorched riparian forests. One can notice how the parched, cracked plains begin to soften as moisture returns to the deep soil layers. The process of healing the landscape is only gaining momentum. They are being reintroduced into specific geographical zones that were previously classified as completely lifeless environments. In these regions, the trees have vanished, the once steady flow of water has ceased, and the salmon populations have disappeared entirely. At first glance, the restoration of such a barren wasteland seems impossible, but in reality, the biological impact of a single colony can transform an entire watershed. Farmers who spent decades exhausted from legal and physical battles over every remaining inch of water now observe a shift in the local water table. The equipment of nature operates with silent, relentless efficiency. How can these genius ecosystem engineers bring barren lands back to life using nothing but mud and timber? The answer lies in the way their dams slow the velocity of the current, allowing sediment to settle and water to seep into the underground aquifers. It is visible how the stagnant pools created by these structures filter impurities and create cool thermal refuges for aquatic life. But this is just the beginning of the environmental transformation. Everything only gets more complicated as the population expands. What specific management protocols must humans implement to ensure that this return does not transition into a new local disaster? Because the uncontrolled flooding of infrastructure or agricultural fields remains a significant technical risk, specialized flow devices are installed to regulate pond levels. The camera glides along the reinforced culverts where hidden pipes bypass the dams to maintain a balance between human needs and the rodents' construction. It only looks obvious to let nature take its course, but in reality, active monitoring prevents the flooding of nearby transport corridors. The secret behind one of the most remarkable biological comebacks in nature is now being decoded through careful observation of these hydrological changes. The process of rewilding moves from the experimental phase into a standard practice for land management. Thus, the restoration of the river systems reaches a stable state, allowing the environment to move toward the next stage of maturity without haste. 70% of the riparian forests in the Pacific Northwest have been consumed by a combination of record-breaking heat waves, relentless droughts, and massive wildfires. Why is this sudden ecosystem collapse occurring with such unprecedented intensity? At first glance, it seems like a localized seasonal phenomenon, but in reality, the survival thresholds for entire species are being surpassed. Summer water temperatures now rise to levels that physically destroy salmon eggs and create thermal barriers that completely block the migration of adult fish. The crisis extends far beyond the borders of Washington. Nationwide data indicates that the United States now ranks among the countries with the fastest declining river systems on the entire planet. The Mississippi River serves as the primary example, acting as the central artery for 40% of the nation's total landmass. One can notice how centuries of human intervention, including the damming of rivers, the construction of massive levees, and the carving of artificial channels, have distorted natural hydrological flows. This engineering has led to a recurring environmental catastrophe. Each summer, a massive dead zone forms in the Gulf of Mexico due to the influx of industrial and agricultural runoff. It is visible how nitrate and phosphorus levels reach 3 to 5 times the established safety limits in these waters. The process is only gaining momentum as it creates a suffocating, low-oxygen water mass that spans from several thousand to over 20,000 square kilometers. Life cannot persist in this hypoxic environment. The upper Mississippi alone has lost nearly 50% of its historic floodplain forests since the 1800s. This erasure of what was once one of the richest biodiversity hotspots in North America triggers a specific chain of events. Transition to the next level. Forests burn and then vanish, causing the soil to erode until massive mudslides follow. The water turns toxic and the land itself eventually collapses. During the dry season, up to 70% of the Yakima River's flow consists of recycled wastewater. One can notice how this flow becomes heavily loaded with nitrates, phosphates, and pesticides under the summer sun. The river transforms into a boiling cauldron of toxic algae where survival for native organisms becomes impossible. Humans have attempted to find engineering solutions more powerful than previous interventions, constructing a massive reservoir to capture dissipated disappearing water remains a primary proposal. But this is just the beginning. The financial cost for a single basin ranges from $500,000 to $2 million. In exchange for this investment, entire landscapes are carved open and the remaining ecosystems are further disrupted. Diversion projects for major rivers remain another option. It looks superficially simple on paper, but in reality, these projects are almost always halted by dense layers of government regulations. Every single meter of pipeline must survive environmental reviews as grueling as a complex asylum application. When large-scale engineering falters, some have tried to imitate nature by building artificial beaver dams in states like Utah and Oregon. Everything only gets more complicated when analyzing the success of these structures. A 2017 University of Idaho study revealed that just a few heavy rainstorms can knock these fragile wood and mud structures apart. They require constant, labor-intensive repairs and fail to replicate the complex ecological functions provided by living beavers. The material and effort spent on these imitations highlights the difficulty of restoring a system that has already reached the point of collapse. 400 million was the estimated population of beavers before human intervention began to systematically dismantle the continental water networks. Why did this massive biological infrastructure collapse so rapidly? The answer lies in the 16th century, when waves of European trappers began an aggressive expansion across North America to satisfy a relentless demand for pelts and castoreum. A sudden and inexplicable shift in global fashion trends led to the rise of the beaver fur hat, which served as the primary catalyst for a demographic catastrophe. Within only a few centuries, the population plummeted to between 10 and 15 million individuals, representing a decline of more than 95%. The environmental consequences were immediate and structural. One can notice how a single ecological error triggered a relentless cascade of larger systemic failures. It only looks obvious that engineering can replace natural cycles, but the removal of beavers proved otherwise. Relying on the belief that human construction could outperform biological systems, engineers began to straighten winding streams and pour heavy concrete into natural riverbeds. These modifications forced water to move at maximum velocity through the landscape. The equipment moved earth to create rigid channels, but this efficiency backfired during seasonal shifts. In the winter months, these straightened paths produced violent flash floods that the land could no longer absorb. By the time summer arrived, the same rivers transformed into completely dry basins. Why is the functional design of a beaver dam so critical to the stability of a valley? At first glance, the structure appears to be a chaotic pile of timber. In reality, each dam functions as a highly sophisticated natural water storage station. The barrier actively slows the current, allowing the equipment of nature to trap sediment and cool the water temperature while expanding nutrient-rich wetlands. Before the Methau and Yakima regions began to dry out, these valleys were supported by nearly 40,000 beaver dams. These structures operated 24 hours a day at zero cost, maintaining a complex network that no modern industrial project could ever replicate. The process of restoration began with a proposal that initially sounded nearly ridiculous to those accustomed to concrete solutions. Ecologists and farmers reached a rare consensus almost instantly when confronted with the historical data of the region. They were forced to admit that the natural solution surpassed any human-built hydraulic structure. One can notice the slow movement of water as it permeates the soil near these biological pump stations, recharging the local water table. It is visible how the cooling flow stabilizes the local climate of the riverbed. When the beavers were hunted to near extinction, it was as if an entire interconnected power grid had been unplugged, leaving the landscape without its primary regulatory mechanism. No human-built structure can compete with a system that has been refined over millions of years of evolution. The transition back to natural management represents a shift in technical priority. 40,000 dams once provided a service that ensured the survival of the entire valley ecosystem. Now, the reintroduction of these animals allows the biological pumps to restart their ceaseless rotation of resources. The water network begins to stabilize once more as the current is broken by the precisely placed timber and mud. From here, the transformation moves to the next phase of processing, as the land begins to retain the moisture it had lost for centuries. Thus, the ecosystem reaches the standard required for the further stage of recovery. $1,500,000 is the total investment required for the relocation and maintenance of a single pair of beavers within this specialized ecological framework. Why would such a specific financial figure be assigned to a biological relocation? A single artificial dam of modest size can cost 15 times more than this biological alternative, while failing to provide the same self-sustaining environmental benefits. But the economic efficiency of the Methau Beaver project is merely a byproduct of a much more complex operational structure. The process of ecological restoration transitioned from traditional mitigation to a sophisticated relocation system in the year 2008. Rather than utilizing lethal methods to manage beaver populations in suburban zones, engineers and ecologists established a rigorous intake protocol. This begins with the deployment of humane traps, followed by a comprehensive health assessment of each animal. One can notice how technicians surgically implant tiny global positioning system chips to monitor long-term movement patterns. Each individual receives a unique identification name and a corresponding record in the tracking database. Transport occurs in specialized trucks designed to move the animals into the Methau and Yakima highlands. This is just the beginning. It seems simple to move a semi-aquatic mammal from one location to another, but in reality, beavers are highly susceptible to psychological stress and physical injury during transit. To prevent panic, handlers immediately cover the transport crates with opaque materials to limit visual stimuli. Inside the vehicle, the equipment maintains a cooled environment provided by specialized ventilation and water systems. Fresh branches are placed within the compartments to allow the beavers to engage in natural chewing behaviors, which serves to regulate their heart rates during the journey. The process is only gaining momentum. Upon reaching the rugged terrain of the highlands, the team manually carries each crate to the precise edge of the freshwater stream. The camera glides along the water surface as the doors open slowly, ensuring the animal exits at its own pace without external pressure. Everything only gets more complicated when considering the territorial nature of the species. Despite these challenges, the data recorded by the year 2020 indicates a massive transformation of the Methau Basin landscape. Over 300 beavers were successfully integrated across more than 60 distinct sites. One can notice how the success rate reached 70%, a figure that highlights the precision of the low-stress handling techniques. The project concludes this phase with a proven model for low-cost, high-impact environmental engineering. The restored habitats now function through natural cycles, allowing the landscape to stabilize without further human intervention. These biological engineers have returned to their ancestral territories to perform the work that heavy machinery cannot replicate. One species demonstrates a level of territorial dominance that makes their collaborative impact on the landscape truly remarkable. Why did scientists initially expect these creatures to perform only minimal environmental maintenance? At first glance, it seemed that the beavers might simply occupy the territory, consume a few branches, and construct perhaps one or two small-scale dams. But in reality, they surpassed all expectations by systematically resurrecting an entire desertified ecosystem through their innate engineering drives. The process is only gaining momentum. Beavers do not engage in dam construction for aesthetic purposes, as every action is calculated for survival. By raising water levels, they create a liquid barrier that shields the colony from predators like coyotes and lynx. This expanded depth serves a critical mechanical function, providing a stable and protected nursery environment for kits during their most vulnerable developmental months. It is visible how the water spreads across the parched earth, allowing roots to regain moisture as grasses begin to return to the surface. 36 weeks after their initial release into the environment, the first physical structures begin to appear. These are modest formations standing only 60 to 90 centimeters tall, looking rough and unassuming against the flow of the current. However, the physical power of these dams has nothing to do with their vertical height. The true strength lies in the specific physics of the structure and the way the materials are integrated. A beaver dam begins with a foundational framework of large branches, which are then layered with smaller sticks that are interwoven like a form of biological rebar. This skeleton is packed tightly with mud and stones, creating a semi-permeable barrier. One can notice how the water does not stop entirely, but slows down, reducing the lateral pressure and allowing the liquid to seep gently into the surrounding soil. This slow and steady seepage creates underground water bands that stretch for hundreds of meters away from the stream bank. It gets more complex further on. This subterranean effect is so stable and technically complex that even multi-million-dollar irrigation systems struggle to replicate its efficiency. When these small dams hold water in the soil for a sufficient duration, a chain of physical transformations begins to spread throughout the landscape. Stable moisture levels actively cool the ground temperature, allowing bacteria, earthworms, and insects to return to the topsoil. A rich layer of humus forms, creating the nutritional foundation for a habitat that supports more than 80% of the wildlife found around each wetland. The shade provided by the regenerating forest canopy ensures that stream temperatures remain below 20 degrees Celsius. This specific thermal limit is the survival threshold for salmon eggs. As a direct result, the density of juvenile Chinook salmon in areas managed by beavers is 5 times higher than in regions without such structures. The survival rates from the egg stage to the fry stage rise from 27% to 33% under these conditions. Everything only gets more complicated when human-made alternatives are introduced. Artificial beaver dam analogs, known as BDAs, are designed to recreate these specific ecological benefits. At a single stream located in Oregon, more than 120 of these artificial structures increase the survival rates of juvenile steelhead trout by over 50%. All of these environmental gains stem from the tireless engineering of a single species at a cost that is nearly zero. A technical report from Okanagan County indicates that artificial restoration projects are 40 times more expensive than allowing the beavers to perform the labor themselves. After 3 years of operation, a single stable dam can save farmers between $3,000 and $7,000 during each dry season. Even with these metrics, the success observed in the Methau and Yakima watersheds does not hide the fact that these animals are not a universal solution for every landscape. The material is ready to move to the next processing phase without haste. Millions of individual beavers remain distributed across the globe, yet the most intense points of friction between these animals and human activity occur on agricultural land. Why do these natural engineers pose such a significant threat to modern farming? It only looks obvious that they are simply building homes, but in reality, their instinct to fell timber and construct barriers makes no distinction between worthless brush and high-value fruit orchards. This lack of discrimination turns a natural behavioral trait into an expensive economic liability for landowners. The process is only gaining momentum once the first branch is placed. A single dam constructed in a suboptimal location can trigger a chain of mechanical and hydrological failures across the landscape. One can notice how agricultural fields become saturated as drainage pipes and irrigation canals are obstructed by debris. The equipment gradually fails to function when water levels rise unexpectedly, inundating rural roads and damaging the very infrastructure designed to manage water flow. Transition to the next level. During periods of heavy atmospheric precipitation, the structural integrity of these dams is put to the extreme test. It is visible how a failed barrier releases a sudden, concentrated surge of water downstream. This creates a high-velocity flood wave that moves with enough force to overwhelm local creeks. For communities situated along these small waterways, such a surge represents a localized but severe catastrophe. It does not end at this stage. Because of these physical risks, the strategy of simply releasing beavers into the wild without oversight remains completely unrealistic. Urbanized environments that lack a consistent supply of woody vegetation or permanent flowing streams are physically incapable of supporting a stable population of these rodents. At first glance, the environmental benefits seem clear, but in reality, the biological requirements for their survival are rarely met in developed zones. Legal and social barriers create an additional layer of complexity that hinders restoration efforts. As many as 40 separate states in the United States currently operate without clear, standardized beaver protection policies. Consequently, the success of any reintroduction program depends entirely on the shifting landscape of local regulations and the specific level of community support available at the time. Everything only gets more complicated when ecological objectives collide directly with immediate economic interests. Without centralized coordination, these conflicts between conservation and commerce can escalate into irreparable disputes. While beavers are not a universal solution applicable to every possible terrain, they remain categorized as one of the most successful ecological restoration models of the 21st century. The material impact of their presence continues to shape how scientists approach the recovery of entire ecosystems. Thus ends one of the key stages of understanding the complex balance between human industry and natural engineering. 28,000 barrels of oil leaked into the environment near the village of Little Buffalo in Canada during the year 2011. Such a massive spill threatened to transform the surrounding ecosystem into a permanent disaster zone. Why did the oil fail to reach the main river downstream despite the slow mobilization of human emergency crews and heavy equipment? At first glance, it seems impossible for a spill of this magnitude to be halted without industrial booms and suction pumps. But in reality, a pre-existing natural beaver dam acted as a physical barrier, successfully blocking the advancing flow of toxic crude while specialists were still coordinating their initial response. The effectiveness of these natural structures is not limited to sudden accidents. One can notice how beaver ponds in the Chesapeake Bay region of the United States operate as massive autonomous filtration systems. These aquatic zones are capable of removing up to 45% of the nitrogen that typically triggers destructive algal blooms. The process is only gaining momentum. To achieve this same level of chemical purification, modern wastewater treatment plants must spend millions of dollars and maintain complex mechanical operations 24 hours a day. It is visible how the scale of these biological structures challenges human engineering on a global level. In Wood Buffalo National Park, located in Alberta, Canada, a single dam stretches for 850 meters, which is more than half a mile in length. This distance exceeds the span of the famous Hoover Dam. Researchers who have studied the site estimate that the construction required the labor of 7 consecutive generations of beavers to reach its current dimensions. It gets more complex further on. This persistent engineering demonstrates a level of precision and long-term planning that exists outside of human technological capabilities. It only looks obvious to assume that every environmental solution must originate from high-tech laboratories or multi-billion-dollar industrial projects. In reality, the natural world possesses established mechanisms that do not require reinvention. The story of these ecosystems confirms that nature primarily requires the opportunity to function without external interference. The equipment gradually moves away, leaving the landscape to its original architects. If a small rodent can successfully revive a dying river system, then the focus shifts toward a deeper understanding of the land and the natural flow of water. Observations of these successful restoration models suggest that biological processes can outperform expensive artificial alternatives. This marks the conclusion of a significant shift in how ecological recovery is understood in the 21st century. The flow of life continues its movement within the restored channels, operating as it has for thousands of years. From here, the model of nature-driven restoration moves into a phase of quiet stability. Thus ends one of the key case studies in modern environmental recovery.